All right, welcome to the ML Performance Reading Group at the Luther AI Discord. Today, Vipul is presenting a survey of quantization formats. So, with that, I will hand it over to you.
Yeah, thanks. So, I'm presenting this paper, which is survey of different quantization formats and techniques, calibration techniques, I guess. And it's, I think it's the latest survey paper on quantization that was written, even though it's not 2023. So yeah, let's get into it. Um, just to motivate why quantization, the paper gave two main reasons. Like the first one is the historical reason of everything that we interact with the data. It's all real valued, but on digital computers we need some discrete representation. So as soon as we do any sort of computation, we need to have a limited precision representation of whatever real value there is. And a reason which is more relevant nowadays is that we have these very, very big models, but we want real-time inference and we want to ensure that we can run them on edge or in a resource constrained setting, which requires low energy. And the observation that the paper made about deep learning models that has allowed us to come up with different techniques is that the deep learning models are over parameterized. So turns out we can get rid of a lot of weights, a lot of precision, and just compress the model quite a bit before we see degradation in performance. And the paper had a few brief survey or a brief paragraph or two about different techniques and why quantization is suitable in the regime of low data and low compute. So I'll also give a brief overview of that. Like one obvious thing was if the models are over parameterized, so then let's just get rid of some parameters. And that's what weight pruning people do. But the problem there is if you do pruning randomly or in an unstructured manner, it will give rise to sparse computation graphs, and GPUs traditionally have not been good at sparse computation. Although recently there are new sparse tensor cores like TF32 and different tensor memory layouts like Marlin and all those things that help with sparse computation, but still it's not a very easy solution. And another solution is just to compress the model by duplicating the knowledge or distilling the knowledge into a smaller model. And you would take, like in this scenario, you would take the larger model and you would take the log probabilities from that larger model and use that as a teaching signal to train a much smaller model and hope that the knowledge is transferred. But it's very costly in terms of compute and data. And this makes quantization a very natural or easy to implement solution for inference because it can be done with very little data and very little compute. And yeah, that's just the big picture motivation of why to even bother with quantization.
Wait, can I ask a
And
quick question on the previous slide?
yeah,
On the
mhm.
sparsity, you mentioned how things like Marlin or like 2-4 sparsity, these like structured forms of sparsity, can be efficient for computation, but not random sparsity, or like random, semi-random like weight pruning. Is there, do you happen to,
Mhm.
do you remember any like figures or any kind of like how much less efficient? Like, is it like the actual like T-flops achievable is like lower or like what, do you know any more details about that?
Mm, can I give you a figure or something? Mm, I actually I mean, I have seen flops in Torch or documentation itself, like, or yeah, or Marlin.
Mm-hmm.
But like, there's it's it's such a thing which is like very hardware and situation dependent. So I haven't seen any figure or something that has made generic or general broad statements about it. But yeah, I mean, there's the there's the original TF32 blog, and I think it has a comparison for the uh I think the throughput comparison and stuff. But yeah, it's very like detail dependent in terms of which some layers the sparsification might actually not have a lot of impact. Some layer it might have some impact. So yeah, like I don't know if I can share like a generic statement on it.
Hmm.
Like what exactly are you looking for in terms of this?
Okay. Yeah, it's just not intuitive to me why like setting some values to zero in the tensor
Hmm?
would affect performance negatively, unless there's more to it than that. But isn't I think just pruning you like and somehow intelligently decide what uh what weights to set to zero.
Well,
Weird.
yeah, yeah. It's I mean they like the paper also talks about saliency, right? Like using saliency to figure out which weights are the least
Mm-hmm.
impactful, and also then and just setting those weights to zero.
Mm-hmm.
So yeah, but I think it's a big question of circuit probing. Like I think Harvard is a good guy to comment on that. But I believe like even probing people and the whole lottery ticket hypothesis people are also asking the same question. Like, is there a good method to figure out which weights to set to zero and which to not set to zero? And I think it's like a NP-hard problem or something. Just because there's like as
Interesting.
uh yeah, as the models get deep, it's just the combinations that are possible with one weight of one layer going to zero and its impact down the line. It's very, very high. Like if the combinations are very like large in number, so just people just do just node attribution or saliency calculation where they like perturb the weight value of one particular node and see what's the impact on the loss, like the gradient of the loss. Does it
Mm-hmm.
But yeah, like from systems perspective, it's like either it's structured, semi-structured, or completely unstructured. And um if it's unstructured, then it's like difficult to actually implement it, right? Like 2:4 or whatever sparsity that you might implement in the memory layout. It's going to be difficult if it's like there's no a priori information. But if you make it too structured, then it's like it's just difficult to retain performance. That's what people have said. But yeah, I don't know if there's like good theoretical a good theory behind it, like a principled way
Mm-hmm.
to make like those art. Yeah.
So just to
Yeah.
clarify, I just want to clarify the phrasing here. When you say sparse computation is costly, do you just mean, are you talking about from like a model quality and not systems level performance, but like the model performance itself is costly? Or do you mean like the actual? Because to me it seems like, a completely unstructured pruning would just have like flat for performance, like some would be zero, but it's not done in any way where the memory layout can be like natively handled by the hardware in some accelerated fashion, like with like 2-4 sparsity
Mhm.
or something. It doesn't see, I can't picture a scenario where performance would be like negative, like costly. Um, does that make
So
sense?
I didn't mean it. Yeah, I get what you're saying. I meant it from a systems perspective, not like a model performance perspective, because
Mm-hmm.
the cost that I am talking about here is that you're doing a lot of flops, which is just zero weights getting multiplied by some activation, and
Mm-hmm.
it's the better phrasing is that a lot
So
of
you're saying it's like
computation can
wasted.
go waste. Exactly. Yeah.
Okay, so okay,
Yeah.
that
So
makes more sense. Got it, got it. Okay, cool.
yeah. Yeah. That's a good point. Yeah. Like wasted is a better phrasing than costly. Yeah.
Got it.
Okay.
All right, thanks.
Mhm. So yeah, now to the next thing, which is like we know that we want to do quantization, but the thing is, in a model, there's three things in reality. One is input, another is the weight, and another is the inner or the hidden activations. If we generalize the concept of activations or inputs to the model, and like we can consider activations and inputs sort of similar, like for a corresponding like a layer in between the model. And then the question is, do we just quantize the weights? Do we just quantize the activations, or do we quantize them both? And what actually happens down the line by making these single neuron level decisions? So here, what we want to consider is two things, which is storage and calculation precision. And what I mean by this is the precision in which the weights are stored in memory that might be different from the precision in which the weights and activations are multiplied together, like a matrix multiplication happens uh, on a CUDA core or TF or on a tensor core. And this is something that we want to keep in mind because it impacts the model's arithmetic intensity, which I'll talk about in next slides. But just looking at the left-hand side of the slide, if we look at the top A part, the weight-only quantization part, this this is a good overview of what actually happens in a like in any MATML op when we quantize. So if we consider the inputs or the activations to be FP16 and the weight is quantized to int8, what will happen is that the weight will actually be upcast to the precision of the activation. So this is what the dequantization operator is doing. And even though the weight was an int8, the actual calculation, the matrix multiply or the matrix vector multiply, that will happen in FP16. And similarly, the bias will be upcast and the bias addition will happen in FP16 and the output will be in FP16. So here we can sort of, already get the plan, like get an idea that the representation is in int8 of the representation of model, but the actual calculation and the activations are in 16. And on the other side, you can have actual calculations as well in lower precision, which is instead of the weight getting dequantized, you'll have the activations getting quantized and the operations being in int8 and again the bias addition being in int8 and then the output if we want it can be in fp16 or if we know that the next layer also is good with int8 inputs and stuff then we can keep on outputting int8. Yeah, so this is like a core part of quantization and that like something that gets hidden away sort of, and I just wanted to emphasize that. And it's important because in the next slide, like I was saying, the arithmetic intensity, or in like simple language, the the scenario of inference, whether we are limited by the flops or the compute, or whether we are limited by memory access, that is critical in deciding whether we want to do weight only quantization or weight and activation quantization. So if we do weight only quantization, then suddenly the memory accesses instead of it being for 16 bits, it's now only for 8 bits, and hence we can fit more weights into the same bandwidth. And this is really good for memory bound situations because your memory cost, like memory access cost, has gone down. But if you are limited by compute and the operation, then it's actually the weight quantization won't help you a lot for compute bound situation. It might actually add an overhead for dequantization. So here you want the activations to also be quantized so that you can take advantage of cores which are more. which have more throughput for low bit. And there is a caveat here for real versus simulated quantization that we'll get to later on. But generally, the GPU will be faster and have a higher throughput for 8-bit flop as compared to 16-bit flop. It depends on the GPU, but we can sort of, for the newer GPUs, we can make the same. So yeah, this is like the decision of what to quantize. It depends on compute and memory bound, and people generally write it as A, X, W, Y, where A is the like this is activation quantization bits, and this is the weight quantization bits. Um, if you want, I can actually let me show you something cool. The I wanted to actually I wanted to get um the this point across by using like a table that is there in NVIDIA's 5090, I think. Oh yeah. So I hope you guys can see my screen, but yeah, this in this table you can see there's different rows corresponding to actual precision and whether the actual precision of the flops or the computation, whether the computation was done in FP4, FP8, or FP16. And for the devices that support it, we can see that FP4 has a higher flops as compared to FP8, as compared to FP16. So yeah, like if we do computation in lower bit, that is the activation is also in lower bit, and we can get more throughput. Yeah, yeah, something cool. Uh, Let me continue. Yeah, so we know what we want to quantize, we know why we want to quantize, but when it comes to how to quantize, most of the people out there do this affine quantization, which is a very simple mapping from the real values R to the quantized value QR or R tilde or R hat using this Q operator, which is the quantization of the rounding operator. And it involves a simple division by something called the scaling factor to scale a large input range into a small input range, and something called the 0 point, which is this D. Uh, so given this input R, we divide it by some scale to compress the total range of the inputs, and then we shift the range by some Z to fit it in our given range. So yeah, this is generally what's done. I think Torchio also, like most of the quantization implementations are affine quantization. So yeah, this is the bread and butter of quantization, I guess. There's a lot of different ways in which this scaling factor and 0 point can be determined, and these different quantization methods, like they're all different types of calibration methods, like stuff like AWQ, HQQ, all these different methods, they apply different loss functions almost, or different ways to solve this problem of making sure that the quantized representation are the same or close to the real representation. Yeah, but we won't get into this. We won't get into that. We'll assume that somehow we know the scaling factor and the Z zero domain, and now what can we do? So, yeah, get into that. So, before I go into this, so like all the different there's like three different scenarios or um methods of quantization that arise due to different choices of scaling factor and 0 point. And yeah, the next three slides are going to be about that. So, like the first is what I describe in the paper as uniform versus non-uniform quantization. So, in the affine quantization, if we are changing the rounding operation based on the input value r. So the value is closer to zero. They need more precision because a lot of that's just a characteristic of a lot of computation. So smaller numbers need more precision and larger numbers don't need as much precision. Then you don't want the same scaling factor for across the whole R input range. So if the scaling factor depends on the input, then that's something that we call non-uniform quantization as compared to a constant scaling factor for all the inputs, which is uniform quantization. And similarly, not similarly, but another thing which is the 0 point. So if so at the top of this at the top part of both of these diagrams, you'll see a number line with R written on it. These are the real inputs, and at the bottom, it's the quantized inputs. And alpha and beta here represent the scaling range, where alpha is the minimum bound of the input that we are like mapping to a quantized range, and beta is the maximum. It, there's more nuance to how it's calculated and all of that, but yeah, like roughly you can say that. So if we want a value in the quantized range, say that value is minus z, map to the zero of the input range, then this is where the input is divided into unequal parts or asymmetric parts. And yeah, this is asymmetric quantization where you actually need to keep a track of the 0 point and have a mapping between how the 0 point is mapped to the original input zero. But you could also have something where the input zero is mapped to the output zero, and here z is zero, so you can get away with that one flop or one minus z calculation. So this is like more efficient in terms of hardware, although people have worked around this. But yeah, so this is symmetric versus asymmetric, like whether you want equal weight to both the negative and the positive numbers, or do you want to divide the input in unequal parts? And I think the paper gives a nice example of ReLU and other such functions which are asymmetric in their inputs, like everything is greater than zero. So it will be a lot of ways to map the zero of input to the zero of the output quantized. We can just map the zero of the input to say minus 128 since we already know that everything will be greater than that. So yeah, this is symmetric and asymmetric. And the last one is dynamic versus static. And I've also added the simulated versus real quantization, which is an orthogonal concept here, but yeah, they're sort of related. So I'll like let's just put it in together. So till now I've been so both these and these are mainly like these and these they depend on S and Z, and we there's like two ways that you can determine S and Z, which is one is that you pre-compute them and you just store the scaling factor and the 0 point uh, based on some known a priori data. And that is what you can do for weights because weights of a model after training are fixed and they won't change with respect to input. So you can already get their distribution and determine the scaling factor and zero on the 0 point. But for activations, you have a choice whether you want to calculate the scaling factor and 0 point on the fly or dynamically for each input, or do you want to use some a priori knowledge of activations and inputs to fix your activation and activation scaling factor and 0 point? So yeah, that's the dynamic and static 0 point. Oh, sorry, dynamic and static quantization where the scaling factor and 0 point are they fixed and predetermined or are they calculated on the fly for each input? And like a very natural jump to this from this to this diagram below. is this notion of simulated versus real quantization. So on the left hand side, we can see that the weights and activations are both 32 bits, and multiplication, the flop also happens in 32. So both the representation and the calculation is in the same precision. But if the representation is in four, so both for the weights and activation, now like representation is in int four, but the hardware doesn't have any support for int four calculation. So what do I mean by this is like, let me go back to that. Yeah. So if you look at all these rows like FP4 with FP32, FP8 with FP16, it's NA. Like the 1390 GPU, it simply cannot do those computations. Like it doesn't have native support, but 1590 has. So you could be in a situation where you might have the quantized weights in Int4, but the hardware doesn't support. It only has FP32 slots, even though 1590 will be able to do FP16. So here you will dequantize, and if it's a static dequantization, you'll already have some scaling factors and 0 points stored along with the weights and activations. And if it's not static, if it's dynamic, then there will be some logic in the dequantization to determine the scaling factor and 0 point. And yeah, so you'll dequantize, you'll do the ops, and then if you want to propagate int 4, then you'll requantize. So this is what's called a simulated or a fake quantization. This is what people refer to when they say like, oh, you're doing FP4 on like 4090. Does it even have FP4 cores? You know, I think Blackwell, they got rid of FP4 cores, or no, they got rid of int4 cores. I think you can do int4 on it, but it will be all simulated, so you won't get the access speed up. You'll get the memory access benefits, but not the compute speed up. And this is the actual real calculate or the real quantization where the ops the calculations they also happen in four. Yeah. One thing that I was actually confused, and maybe Daniel, you know about this. Like, I didn't get like why anyone would do requantization before like uh, like if the multiplication is in int4, then why do you want to do accumulation in 32? Like, doesn't it make sense to just
Mm,
do accumulation in int4 and then just send it up? Like, I don't know.
well,
Yeah.
I can speak to why they do it in with floating point gems,
Mhm.
which I assume is a similar reason for these like int 4 gems. It's because the accumulation, you're doing a lot of fuse multiply adds and doing floating point arithmetic, accumulating over many, many, many products. You're basically compounding rounding error. And so using a
Mm.
higher precision accumulator like FP32, you can keep your numerics much closer to your baseline, like pure FP32 gem, than if you accumulated in like a low precision like FP8. Your numerics will be much
Mhm.
further off due to the accumulated rounding errors. Um,
Oh,
but for integer accumulation, I'm not sure. I assume it's a similar reason though, but I'm just not as familiar with like integer quantization.
yeah. Yeah, but yeah, that was a good thing to know. Like, yeah, I never like, yeah, I think Torch also has this flags for reduced accumulation, like allowing
Yeah.
reduced accumulation and stuff, right?
Yeah,
Like,
it's called slow
okay.
accum versus fast accum. Slow accum uses FP32 accumulation, and you get more robust numerics. But you can do fast
Mhm.
accum, and it accumulates with something like it's like a custom. I can't. It's like a 22 or 21 bit accumulation setting, like in the register somehow. I can't remember exactly, but they actually had to like reverse. I saw this thing where they like reverse engineered how many bits it was because like NVIDIA didn't publish it or something. I can't remember exactly, but it's faster. Yeah.
Interesting. Yeah,
Mhm.
thanks. Thanks for sharing that
Mm,
part too. Okay. Yeah. Uh, so just to recap, we went through affine quantization, and based on the scaling factor on 0 point, we have these three methods: uniform, non-uniform, symmetric, asymmetric, and dynamic versus static. And then we also talked about, like, we know what to quant, we know how to quant, but are we actually doing the quantization or not, which is the simulated versus real quantization. So it's like the hardware level details of whether quantization is actually happening. Um,
mm,
and yeah, this is the last sort of big picture concept in quantization, which is, we like till now we've just been discussing about a single real value, but that will be very, very computationally, like, expensive to do quantization at a single floating point value. So we always group the tensors via some group size or via some, like, logical sort of, and like the types of tensors that there are. And this is the granularity of quantization. So the paper, I think it goes through these four different methods, like layer, group, channel, and subchannel. So you can have a particular layer which is quantized to FP16 and another layer which is quantized to FP32. So you have this mix of different precisions in the model. And what layer-wise quantization would imply is that all the weights and may and or the activation, not and or, but like maybe even the activation, they'll all share the same scaling factor and 0 point as compared to individual floats. And the implication for that is the performance in terms of the matching of the quantized output with the real input, or with the real output. Like, it can get pretty bad because you lose resolution if the distribution of the weights was non-Gaussian or something. So yeah, they've shown this in this example, which is some some layers might have a distribution which is very, very high resolution, so like a peakier Gaussian, and some layers might have a broad, like a fat-tailed, or like less, less kurtosis, or I don't know what's the word, like a more spread about low resolution weight distribution. And if you apply the same quantization to these different distributions, which is these red lines, red boundary dotted lines that they show, some, like, you lose a lot of information, a lot of resolution for distribution which were not, like, which are very far away from this generic or this dotted line thing. Yeah, you can in their example of convolution net, they were like, instead of doing this layer by layer, or instead of doing it by filter by filter, you can do it at the level of different channels of the filter, I believe. Uh, so, like, different depth or different channel of the filter can have different scaling factor and 0 point. But in general, I think, and even in Torchio for transformers, especially, and linear layers, what I have seen is a simple group size, which is generally 32 or 64, which indicates whether within a single tensor, whether you want to have a single scaling factor for 32 floats or 62 floats or something like that. So yeah, generally you do what they call here sub-channel, or what's generally known as sub-tensor scaling, or sub-tensor quantization. And so yeah, Daniel, maybe you can comment on that, like the different tensor-wise and row-wise scaling options. Yeah, and it's pretty implementation dependent sort of thing.
yeah, the trend I've seen is moving more and more towards more granular and granular scaling granularities. Yeah, tensor wise, and I guess just doesn't work well enough in practice due to outliers and the sensitivity to outliers, because that
Mm-hmm.
will impact the scaling factor for all elements under that scaling group, which can cause a lot of quantization error. Things get, you know, underflow to zero and whatnot. and you lose that information permanently. Essentially, you can't like requant or dequantize a zero, so um, it's gone. So yeah, yeah, this is cool. Did they? So this is all. I mean, they're talking about filters, so it seems like they're kind of this is in the context of like CNNs or something,
Yep.
convolution layers. Okay,
Yeah. Yeah. Yeah.
cool.
They gave a very specific example of CNN.
Mm-hmm.
Although they had another diagram about mixed precision, which was also like a generic ANN. It's like this paper is from 2023, and like ever since nobody has for some reason written a survey on quantization.
Mm-hmm.
So yeah, it's lacking in the newer transformer specific details. Yeah.
It's cool. I
The
mean,
same this yeah
the principles still apply. Yeah.
yeah like the same people, the same group of people. I think this is a lab at Berkeley. They wrote a paper for transformers recently, but it was also it was very
Mm.
broad. It was not specific to quantization.
By the way,
Yeah.
I actually had a question about. So I'm just not as familiar with some of the inference quantization
Mhm.
techniques. I've never been quite clear. I've been meaning to research this forever. Maybe you could just answer for me. When we would want to use like a 0 point, where we're mapping zero to some other uh, value essentially, and doing like that asymmetric quantization. Um, like, is there some sort of concrete example or use case? Maybe you mentioned one and I just missed it, where that's like superior to just symmetric.
Mhm. Yeah. I was also. This is something that I never just thought about, but this paper actually has a nice example of it. Like, if you already know that the weights and activations are going to be imbalanced, like
Mm-hmm.
ReLU or something, then just use asymmetric quantizations, Like, it doesn't
Mm-hmm.
make sense to actually maintain the whole negative elements if you have ReLU. So yeah, like that seems like a pretty clear-cut example of asymmetric quantization.
Mm-hmm.
And other than that, it's also I think it's just the distribution of your weights or quantization or any data, like whether the distribution is skewed or whether it is unskewed. So, like the best thing to do is like the method is simply to plot the distribution of weights and some activations and see what method works best for it. Yeah.
I see. Okay, that makes sense.
So I just wanted to check on time. I think we have what 15 minutes left, or
Yeah,
I think
that's fine.
okay. Yeah, let me. Yeah, I think only MX format the MX53 and stuff is left and a little bit on activity. Yeah. Uh, yeah, like we were till now mainly focusing on given a model with its weight, the weights being constant, and we are simply doing inference uh, after quantization without any data or something. So, like if we just calculate the scaling factor and 0 points from the weights without any data at all, that's like zero shot quantization. But you can also, for the purposes of activation or just for the purposes of better quantization, you can also consider some data, some calibration data. Uh, so the this leads to like different stages in the pipeline when you can quantize. So one is quantization during training, which is quantization aware training. Another is post-training quantization, and then within post-training quantization, there is do you use some calibration data or do you just do zero shot? So, like focusing on the right side for now. So, given a pre-trained model, the calculation of scaling and 0 point, either you can do it by plotting the distribution of weights and just looking at what fits best, or you can actually use some data to um, like for especially for the activations, you can use the data for figuring out what's the range of the activations and what's their distribution, or you can figure out which like you can sort of test the performance of your quantized weight by using this calculation data and then to tweak the scaling factor and the 0 points for those weights based on that. So that's post-training quantization where you have this method of calibration where take some data, you quantize the model, you test with the calibrated data, and yeah, after that you have some quantized model. Another which is quantization aware training, which is something like you're doing activation quantization, for example, and you want to ensure that the PTQ or any quantization down the line, um, it works well. The performance in terms of model accuracy and all those metrics is good. And you can do this by making the model aware of quantization by taking some, like maybe by fine tuning or during the training, you take some training data, you take the weights, you quantize the weights, you do the forward pass with the quantized weight with the training data. And with this, you will get some loss, which is which the loss depending on the quantized weights and the training data. And you can use the gradient of this loss to update the actual unquantized or real weights to reduce the error introduced by the quantization process. So going into more details about this. So what generally you will have is you will have some weights, you will have some quantizers. Given these quantized weights, you will do a forward pass and calculate the loss. And in the original precision, then you'll take the gradient which is in the original precision, and you'll update the original precision weight such that this overall process, the overall forward process pass is more like the loss goes down because of the whole process. So yeah, this is the general flow of quantization aware training, which is yeah, just make sure the original real value weights are good. That if anyone down the line does quantization with our quantizer off, it will work well. One caveat or one nuance here is that as you can see, this quantizer function has a lot of sharp peaks sort of thing. Like it's very difficult to get a good gradient here. And for that, they gave an example of two methods. One is the straight through estimator, and another is stochastic rounding. I think Daniel, we in the paper that we were discussing, quadrant or something, stochastic rounding was also mentioned. They are
Yeah,
essentially just ways to, yeah, they're just ways to estimate the gradient of a quantizer because the gradient is difficult to calculate. So they just replace the they just make the gradient as I like they just make the function as identity function, I think.
yeah.
Okay,
There's
not the gradient as identity. Yeah.
there's one cool thing I can mention here. I can't remember the paper name off the top of my head, but it was a paper on FP4 training, but it wasn't Quartet. It was a prior one. But they had some kind of clever formula that essentially makes like a continuous sort of like not rounded, but basically a continuous differentiable version of that step like staircase looking function you see there and in your quantizer
Mhm.
up. Um, that is very, very close to it, but is smooth and differentiable. And that
Mhm.
allows them to have more precise gradients instead of using straight through estimation. And it made FP4 training more stable, basically, which I thought was really interesting. And the other thing I just want to mention is that QAT becomes especially important as you move to lower and lower bit widths and you're doing like FP4 training.
Mhm.
It becomes critical to achieve, like stability, like stable, usable model afterwards.
Yep.
Yeah, yeah,
Yeah. Makes sense. Yeah. Uh, that is a good jumping point. Like what Daniel just mentioned, if before, like there are these new extreme bit quantizations or very low bit quantization methods that are popping up, like FP4, FP6, Int 4, which are going like at a sub byte level, but even FP8 and all these different bit widths. Since there are so many, I think recently a bunch of companies they came up with this microscaling format, which is what they call MX format. And we talked about the group size also a few slides back. So what they do is they group some floating points or some elements of a tensor together, and they make all of them share a single scale, which is this x value and this private element. Yeah, like this came in I think recently. I don't know, but yeah, it's one way to ensure consistency across different hardware and software. So going into a little bit more detail. So like generally, uh, like if you have some input vector, some tensor of scalar floats, what you'll do is you'll divide the scalar into group size subtensors, and for each group size, you'll like take the maximum value, maximum floating point that was there in that tensor, and you'll find the nearest power of two for for that value, and you will divide all the input element vi by that power of 2. So this is the quantization operator, like r divided by scaling factor s, where x scaling factor is the power of 2, which is the largest power of 2 near the smallest power of 2 near the largest value of v, essentially. But yeah, so this is generally the MXFP format that we see nowadays, like MXFP8, MXFP6, S6, MXFP4. It's a pretty simple division of group size by power of two, and yeah, just store it. And when you're doing dot product or anything, what you'll do is you'll do dot product at the level of this group size. And the the Microsoft paper that was there in the event information, I think it has that formula. So it it works out nicely because you can just do dot product of the pi elements and separately multiply both the scaling factors together. I think I can show that. Mm, yeah, it works out nicely because you can just take the scaling factors outside and do the actual dot product in low bit. So you can use the low bit tensor cores, do the operation there, and then just do the separate multiplication. Uh, it's nice. It's like computational efficient. This is like a very broad MX format overview, and the the Microsoft paper that I shared, it has details on the individual formats. There's also the OCP PDF for that. But yeah, the big picture thing or the main thing that one needs to keep in mind for MX formats is this EXMY sort of notation, which is how many bits are you allocating for the exponent and how many bits are you allocating for the mantissa or the decimal part or the precision part. Um, you, one thing to note is it assumes that one bit is given for signed. So these are all signed floats. And yeah, what what you'll see people doing is for forward pass, they'll use something like E5M2, where the range is high because the exponent is high. Like the range is from what 57,000, like plus minus that. But you don't need as much precision, so you can reduce the mantis a bit. But for backward pass, you use a lower range, which is plus minus 448, but you get more precision out of it. There's like three mantis a bit, so you get more precision, which is the goal. But not but yeah, this is like the overview of MX format. Like MX format is pretty standardized in terms of all the MX format. They all have a mandatory block size of 32. So 32 floating points need to be combined together, and they all will share an 8-bit scaling factor, which is a power of 2. Like E8M0 is essentially a 2 to the power x, uh, where maximum I think can go what 2 to the power 8 or 2 to the power 8 minus 1, something like that. So yeah, and this element bit width represents the individual PI elements of it. So in MXFP8, the PI will be 8-bit, in FP6 6-bit, the 4, and then in 8 8-bit. So yeah, one thing to note here is that oh, before I do that, one motivation for this is obviously nowadays we have these tensor cores where we can take advantage of float, low bit flops to get more throughput. Another is if you are on edge, your microcontroller might not even have floating point instruction support. So that's when you are bound, you're limited to use int instructions and MXN formats. And another is just sub-byte precision that sub-byte quantization and sub-byte D types that you might need for on edge. Yeah. One interesting thing here is that MXFP4 in practice gives really bad quality because it allocates 2 bits to exponent and only 1 bit to mantissa, and the group size is 32. So I think MobiCham, like the GPU mod, he said this. For this reason, NVIDIA came up with their own NVFP4, which has a much smaller group size, like half group size, which is a 16 value block. And yeah, it apparently helps a lot with maintaining the quality. On Blackwell, you also have a P4 tensor core, so you'll get the high throughput as well. Yeah, is that it? Yep, that's all. That's all. Yep.
Cool. I can
And yeah.
can I add a
Mhm.
couple interesting little notes on MX
Yep.
types? One thing someone told me I thought was an interesting way to think about the you were talking about like how FP4 empirically is shown to have like worse results. Um,
Hmm.
they and but NVFP4 is a bit better because it has like a FP what is it FP is it the scale is it FP16 or FP32? It's not E8M0, right? Or is it
Yes,
FP8?
it has
FP8.
yeah it has two level scale. So first it does global scaling in FP32 and then group wise scaling with FP8.
Right,
It's
right.
like a
Okay.
multi-level scale.
Okay, yeah. So somebody from NVIDIA told me basically their research has shown that between the actual value of the element, like the D type of the value, and the scale, you need to have some number of mantissa bits allocated to it. And in MXFP4, there's simply just not enough, as you just noted. There's like one. But
Mhm.
with something like NVFP4, between the scales, and the value, there's like sufficient ability to express these kind of like finer grain movements.
Mhm.
Um,
Yeah.
and so I thought that was kind of a cool way of thinking about it. And then other thing, just like a fun implementation detail, or not so fun if you're me.
Mhm.
Basically, for to actually use these, like you see like MXFP, and you're like, oh, I just like the nearest power of two, and then it's like E8M0. That's my scale, and I can just scale down and then rescale back up after the gem, like fairly easy. But it's actually much more complicated on the implementation side because to actually use the tensor cores with this particular numerical format, you have to have the scales in something called like blocked swizzled format, which you can Google. It's this super odd format where basically you need to take your scales and the number of rows in your scaling tensor or your scales tensor needs to be divisible by 128, and the number of columns,
Oh,
which would be your actual scales, like there's like one per every 32 elements, for example, that needs to be rounded up to the nearest. It needs to be a multiple of four, and you round up to the nearest multiple of four, and then within that you have these blocks. So now you have this tensor, this like padded tensor, and within these like 128 by 4 blocks, you have to like map. Uh, Basically, there's like this swizzling formula they provide in the NVIDIA docs that maps the elements like specific locations in memory. That that then the scale has to be available in TMEM, I believe, which is a new type. It's not global memory or shared memory. It's like a subset of shared memory that
ah,
has a simpler, closer connection to the actual tensor cores. And so it does, when you do these MXFP8 gems, it does the accumulation in TMEM, and it also stores the scales in there, so they can be referenced during the actual, the FMA and then the rescaling very quickly. And to be usable in that, like basically to actually use the tensor core to actually get a speed up, you need to have them in this special format. And as with anything, like with training, if you have a gem that's say like 1.5x or 2x faster, then all these quantization ops, the scaling, the conversion to blocked format, all these need to happen in a time that is faster than the difference between your BF16 gem and your MXFP8 gem. Otherwise, your MXFP8 ends up actually being slower than BF16.
Mhm.
And so
Yeah.
it's actually like a very like a involved process to make sure all these quantization ops, the block format, conversion ops, you basically need to handwrite kernels for each of these things. Ideally, minimizing, of course, like the amount of data movement happening between GMEM, SMEM, and so on, and making sure that, ideally, like write them directly to blocked format if you can. Um, but yeah, anyways, it's just tricky to use or to get it work. It's much trickier to get working properly with a good performance improvement versus something like just standard like FP8 blockwise or FP8 rowwise because it's such a there's just more quantization. There's more ops that need to happen, and the format itself is much more complicated. Like the memory layout is more complicated. Because even sorry, I know I'm going on for a bit here, but one more thing.
That's fine.
Even the scaling, even the scales themselves, I mentioned that blocked format. Um, it's not even really representable with like a simple shape and stride like you would see in a regular PyTorch tensor. It's in this format that I would describe, or I describe as row of blocks major, which means that I'm talking specifically about for MOEs right now, where you need to do a group gem, where basically each subtensor of your scales, right? Each subtensor you're gonna have a scale for each gem that occurs as part of this group gem, but each subtensor that
Mhm.
contains the scales for that specific gem needs to be in the like kind of like the blocks. These 128 by 4 blocks I was saying need to be in row major format. The blocks themselves, not the actual data within the blocks. Those need to be in the
Okay.
special like swizzled format, but the blocks then need to be in row major format. And then it's only within that subtensor that they're row major. It's row major per subtensor. So my point that I'm making is that it's actually like not easy to express this in just
Yeah.
PyTorch. Like I wrote various like Triton and CUDA kernels to make this work. And finally, after
Mhm.
months of struggle sessions, the past like 3 months, we're getting some solid speed ups, which you will hear about shortly. So stay tuned. But
Right.
um, yeah, this was awesome presentation. This is excellent. Did you have anything else
Yeah.
here you wanted to go at the end, or?
No, I'm like, think I'll be interested in hearing more in the PyTorch conference, like your guys' results. And it's nice to know that it took 3 months and it's not something that people can do within a single day because
Mm,
like it everyone expects that it will be done in a single day because it's just a deep dive. But yeah, it's nice to know that it's actually a lot of difficult work. And yeah, I think like on actual practical sides, Torch AO and Gemlight from MobiCham. I think those are the two frameworks which are actually making MXFP4 and NVFP4
mm,
available, right? There's not a lot of options to actually use these features. So yeah, that's really good.
yeah. I also can. I'll just share blog posts in the chat after this. It's from Cursor. They posted a very cool blog post doing like a deep dive on MXFP8 training for MOEs and the kind of like kernel level and systems level challenges that they encountered getting it to perform well. And you'll understand, I think, more deeply what I was talking about. And they go into much more detail than I did in my short little rant. So I think
Yeah.
people in this call would probably enjoy that. So yeah.
Yeah,
Anyways,
yeah, thanks.
cool. Yeah, thanks for presenting today. That was very useful, even for myself who have had exposure to these things. I got to fill in a couple gaps I had on the inference side, which is awesome. So thank you.
Mhm. Yeah, no worries. Yeah.
All right.
Thanks for everyone's time. Yeah, I'll see you guys on the Discord. Yeah. Thanks. Bye.